Alright, chapter 6, we're continuing on with trigonometry, another chapter of trigonometry, and the first section in chapter 6 is trigonometric identities and equations. Now, I don't know why they call this section equations, because we don't deal with equations. We'll do that in a later section, but we are dealing with identities. What are identities? Identities are statements that are true for all permissible values of the variable. So, for example, an equation is something that's true for just one or two or a few different values. Identities are true for every single value, unless it's a non-permissible value. So just to give you a sense of some of these, and actually more than just to give you a sense, these are the most important identities that you need to know here. There's 8 of them. There's 5 of them, I believe, that we already know. So this is actually, believe it or not, review. The reciprocal identities, we know what reciprocal means. It means when you flip something over. So the reciprocal of a whole number, like 5, the reciprocal of 5 is 1 over 5. So all these reciprocal identities have 1 over. So the things like cosecant of theta, in other words, the cosecant of any angle is equal to, and you know this, we've done this before, cosecant theta is the same as 1 over sine theta. So that's an identity. For any angle that you put in here, this will be true, except, as it says up here in the definition, except for values that aren't permissible. So what value wouldn't be permissible here? Well, if sine theta equals 0, don't write this down, but if sine theta equals 0, it wouldn't be permissible. When does sine theta equal 0? Sine theta equals 0 at 0 degrees and at 180 degrees, which is the same as at pi degrees. Anyway, we'll talk about non-permissible and restrictions in a second. Alright, so that's one reciprocal identity. Another one is that secant theta, remember what that's equal to? It's equal to 1 over cosine theta. Done that before. And the last one of the reciprocal identities is that cotan theta is equal to 1 over tan theta. Okay, we've done all those before. The next two I think we've also talked about. These are the quotient identities. Well, quotient means divide, so these are two identities that involve division. Okay, to help us out with these, we're going to look at the unit circle again. So remember what we've talked about numerous times is with the unit circle, if we draw a angle in standard position and make this little right triangle right here, this point right here, which is on the circumference of the circle, of the unit circle, the coordinates of that point are cosine theta, cosine theta, comma, sine theta. Or the other way you could think about it is this distance here is cosine theta, and this distance up here is sine theta. Forgot the theta sign. And remember, theta is this angle right in there, right? And this is a unit circle, so this distance here is 1. So if we were going to get the tan, if we were going to take the tan of this angle right here, this theta right here, tan of theta equals opposite, which is sine theta, over adjacent, which is cosine theta. Hey, that's one of the quotient identities. One of them is that tan theta equals sine theta over cosine theta, which we've talked about quite a few times. Another one is that cotan theta, well, let's think about this for a minute. If cotan theta is the same as 1 over tan theta, in other words, the reciprocal of tan theta, then it would be the reciprocal of this. Cotan theta is equal to cosine theta over sine theta. Alright, all those 5 I think we've talked about, maybe not this last one, but I'm sure that makes sense because of these two putting together, you get this. The last 3 are called the Pythagorean identities. Guess what you're going to use to find these? You're going to use the Pythagorean theorem. In fact, you only have to really use it once. If we look at this, again, this unit circle and this triangle we've made here, we have a right triangle and we have all 3 sides. We have statements for all 3 sides. So we know that the 2 legs, if we square them, this side squared plus this side squared equals this side squared. A squared plus B squared equals C squared. Or in this case, cosine squared, oh, by the way, cosine theta squared, don't write this down, or you can if you want, plus sine theta squared equals 1 squared, right? Now, when we write cosine theta squared, the way we write that is we actually write cosine squared theta. That's the same. These two things mean exactly the same thing. So this would be sine squared theta equals 1 squared, which is 1. That is one of the Pythagorean identities. Cosine squared theta plus sine squared theta equals 1. All right, if we want to get another one of the Pythagorean identities, here's what we can do. We can divide both sides of this equal sign. So we're going to take the this first identity, this first Pythagorean identity. We're going to divide both sides by, I don't know, let's divide them both by cosine squared theta first. So we're going to divide this everything by cosine squared theta. This by cosine squared theta, this by cosine squared theta, this by cosine squared theta. Now, cosine squared theta divided by cosine squared theta is 1. Sine squared theta divided by cosine squared theta. All right, might not have known this yet. What's sine theta divided by cos theta? Sine theta divided by cos theta is tan theta. So guess what sine squared theta divided by cos squared theta is? It equals tan squared theta. Equals 1 divided by, what's that even say? Cosine squared theta. Okay, what's 1 divided by cos theta? 1 divided by cos theta is secant theta. So 1 divided by cos squared theta must be secant squared theta. This is another one of our Pythagorean identities. 1 plus tan squared theta equals secant squared theta. To get the last one of these, I was going to try to squish it in here, but I've run out of room, so I'll do it over here. I'm going to write this first one again, cosine squared theta plus sine squared theta equals 1. This time I'm going to divide everything, so I'm going to divide both sides, divide everything by sine squared theta. Sine squared theta, sine squared theta, divided by sine squared theta. Okay, cosine squared theta divided by sine squared theta. Well, we know that cosine divided by sine, right here, equals cotan. So cos squared divided by sine squared must equal cotan squared theta. Plus sine squared theta divided by sine theta squared, well, equals 1, equals 1 divided by sine squared theta. Well, again, we know 1 divided by sine theta equals cosecant theta, so 1 divided by sine squared theta equals cosecant squared theta. And this is the final one that we have to worry about. Let's write it the other way around, though. So we'll put 1 plus cotan squared theta equals cosecant squared theta. Of course, order doesn't matter. You could have cotan squared theta plus 1 equals cosecant squared theta. You could have tan squared theta plus 1 equals secant squared theta. And to tell the truth, usually this isn't written this way. I don't think there's any rhyme or reason for it, but usually this is actually written sine squared theta plus cos squared theta equals 1. So if you're talking to your friends from other schools about trigonometric identities, don't be surprised if they say it the other way around. I know that happens a lot, that you're talking about trigonometric identities. All right, strategies for simplifying trigonometric expressions. So what's going to happen is you're going to get these complicated things like this, and you have to simplify them. How do we do that? Well, notice these are not steps. These are strategies. I'm not saying this is always the way you're going to do that. This is one of the difficult, I suppose, things about this is I can't give you a step 1, do this, step 2, do this. There's different strategies you have to try. Sometimes you'll go down the wrong path and you got to try again. So here's some strategies for you. Strategy 1, get a common denominator. So for example, if we had something like sine x plus sine x over cos x, and we wanted to simplify this, one way you might do this is you might want to get a common denominator. In the second expression here, you have a denominator of cosine x. What's the denominator here? It's 1. So just like with regular fractions, if you want to get a common denominator, what is the common denominator first of all? Well, the lowest common denominator of 1 in cosine x would be cosine x. What do you have to multiply this 1 by to get cosine x? You need to multiply by cosine x. So whatever you do at the bottom, make sure you do the top. You have to multiply top and bottom by cosine x. So what's that give us? It gives us sine x cosine x, or cosine x sine x, doesn't matter the order there, plus sine x all over cosine x, because that's the common denominator. Okay? Just like with regular fractions, I'm just getting a common denominator and then adding the numerators, keeping the denominator the same. Your fraction rules always stay the same. Okay, next strategy, not step, but the next strategy that I'll introduce you to is factor. For example, if we had something like sine squared x minus 1. Well, look at this is something squared, take away 1. This is a difference of squares. you could do sine x, take away 1, and sine x plus 1, right? So this is just a difference of squares. It's the same thing as factoring something like x squared minus 9. That equals x minus 3, x plus 3, right? We've done exactly the same thing, a difference of squares. Okay, let's do one more factoring one. What if we had something like cosine squared x minus 4 cosine x minus 12? How can we factor that? Well, look, this is something squared. Then we just have it not squared, and then it's kind of like, this is kind of like m squared minus 4m minus 12, but instead of having m's, we have cosines. But you still do the same thing. This is like a simple trinomial. We put cosine x and cosine x, because cosine x times cosine x is cosine squared x. Then we're looking for two numbers that multiply to 12 and subtract to 4. Oh, it's 6 and 4. Negative 6. 6 and 2, sorry, negative 6 and plus 2 are our numbers. So here you go, we've factored that. Okay, so that's the second strategy. Strategy number 3 is change all terms to sine and cosine. This is often very helpful. So for example, if you have tan x divided by secant x, and we wanted to simplify that. Oh, I don't know what to do. So we'll switch it all to sine and cosine. What does tan x equal? Look up here. Tan x equals sine over cos. So tan x equals sine x over cos x. That's what tan equals. Over secant x. What's secant x equal? Secant x equals 1 over cos x. So 1 over cosine x. Now, what's this big line mean right here? It means divide. So it's the same as this first fraction, sine x over cos x, divided by 1 over cos x, which is the same as times the reciprocal, right? We're going to flip it over. Cos x over 1. That's how we divide fractions. You flip the second fraction and multiply. Yay, look what happens when we do that. It's very exciting. These cancel out, and you are left with sine x over 1, or just sine x. So, do you understand what this has taught us here? This has taught us that if you took any angle and you stuck it in here and here, so tan 45 divided by secant 45, whatever answer you get when you divide those would be the same as if you just put that angle 45 here, sine 45. This is a simpler way of getting the same answer. We've simplified this. This is what your task is going to be today. Okay, last thing you're going to do is you could multiply by the conjugate. I should probably put a the in there. Multiply by the conjugate. Now, do you remember what the conjugate is? I'll give you an example again. If we had something like, oh, this was an example here, and here's another example. If we had something like 1 over 1 minus cosine x. The conjugate, remember when we tried to rationalize denominators? Like if we had 2 over root 3 plus m. Do you remember what we do is we multiply the top and bottom by the conjugate of this, which was root 3 minus m, and you do the same here. That's when we wanted to get rid of the radical sign in the denominator of an expression, right? Well, you do the same thing sometimes when you're trying to simplify trigonometric expressions or identities. You multiply top and bottom by the conjugate. So what's the conjugate of 1 minus cosine x? It's 1 plus cosine x. So we're going to multiply these together on the bottom. And whenever you do the bottom, you got to do the top. So we also have to multiply this by 1 plus cosine x. Okay, let's do that and see what happens. Well, on the top you have 1 times 1, which is 1, and 1 times cosine x, which is cosine x. On the bottom you have, okay, now you got to do mountains and valleys here. 1 times 1, which is 1. 1 times cosine x, which is cosine x, but then negative cosine x times 1, which is negative cosine x, so those cancel. And then negative cosine x times positive cosine x is negative cosine squared x. Okay, now look at this bottom piece here. There's 1 minus cosine squared x. If you look up here, do you see what you could do for 1 minus cosine squared x? That is actually going to come into play right here, because we have 1 minus cosine squared x. If you look up here, if you were to move this cosine squared x, or theta in this case, if you were to move it over, what would you get? You would get sine squared theta would be left on this side, equals 1. We're moving the cosine squared theta over, so you get minus cosine squared theta. Hey, isn't that exactly what we have here? 1 minus cosine squared x, 1 minus cosine squared theta. X and theta are just like A's and B's, it's just different symbols, right? So in other words, this 1 minus cosine squared x here is exactly the same as sine squared theta. So our final answer would be 1 plus cosine x over sine squared x. So you have to also take into account the fact that when you move these things to the opposite side and everything, those are also identities. That's basically only comes into play with these last three here. So tan squared theta is the same as secant squared theta minus 1 if we were to move the 1 over. So there's actually some other identities which are just totally related to these ones that come into play. One thing I'll say about this conjugate step, I did all the questions in this chapter, in this section of your book. I didn't use the conjugate once. So there's often more than one way to do these. Maybe there's a couple of questions you could use the conjugate. I try to avoid it as much as possible. Definitely did lots of these the first three steps. I didn't do the conjugate at all. So if you want, don't worry about it today. Okay, let's do a few questions here. We're going to simplify cosecant x divided by tan x plus cotan x. We're going to determine all the restrictions as well. Okay, so we'll talk about the restrictions in a second. Let's focus on simplifying this first. I think the best way to start with this one would be to switch it all to sine and cosine. So what's cosecant x in terms of sine or cos? Cosecant x is the same as 1 over sine x. Look at your reciprocal identity if you're not sure about that. Divided by, that's that line right there, tan x. Tan x is the same as sine x divided by cos x. Plus cotan x. Well, that's the reciprocal of tan x, so it's cos x divided by sine x. These are both of the quotient identities right here. Alright, now maybe what we want to do is we want to get a common denominator in the bottom here. So we're going to leave the top part, this 1 over sine x. And we're still going to divide that, but let's try to get a common denominator for this. So what's the common denominator there? The common denominator is cos x times sine x, right? The common denominator of cos x and sine x is cos x sine x. So on the bottom here, we're going to have cos x sine x. Now, what do you need to multiply this by, cos x, to get cos x sine x? You need to multiply it by sine x. So you better multiply the top by that as well. Sine x times sine x equals sine squared x. Plus, it's going to be very similar on this side. What do you have to multiply sine x by, the denominator sine x, to get cos squared sine x? You need to multiply it by cos x. Okay, so do the same at the top. Multiply cos x by cos x, you get cosine squared x. Alright, now, let's rewrite this, 1 over sine x. You should notice something right here, sine squared x plus cos squared x. Please get used to that. That is probably the most important of all the identities. It shows up all the time. Cosine squared x plus sine squared x, or in this case, sine squared x plus cosine squared x equals 1. So this is great. All this bit right here is just equal to 1. So we have 1 over cos x sine x, definitely getting a little bit easier looking. Okay, this means divide right here. So we have one fraction, 1 over sine x. We're going to divide it, but let's multiply by the reciprocal. So the reciprocal is cos x sine x over 1. Now you can do some simplifying. This sine x and this sine x cancel out. If you want, cancel the ones or just don't worry about them. You end up with an answer of cosine x. Wow! If you wanted to know what this was equal to right here, you could plug the angle in here and here and here and add and divide and all that kind of stuff. Or you could just put the angle right in there, you get the same answer. So we've simplified this thing down to a much simpler form. Alright, now we need to determine all the restrictions. So you get restrictions wherever denominators equal 0. Where do we have denominators equal 0? And let's look at this first simplified form right here. Look in here. Where we have denominators equal 0. Here's the denominator, so we're not allowed to have sine x equaling 0. It just can't happen. Otherwise you'd be dividing 1 by 0. You can't do it. You can't have cos x equals 0. Otherwise you'd be dividing by 0 right here. You can't have sine x equals 0 here either, but I already have sine x can equal 0. So this is it. These are your two restrictions. You can't have sine x equals 0, you can't have cos x equals 0. Now, when do those two things happen? Well, remember unit circle. 1, 0 is this point, 0, 1 is this point, negative 1, 0 is this point. 0, negative 1 here. We can't have sine x equals 0. Where does sine x equal 0? Sine x equals 0 right there, right? The second number sine. And sine x equals 0 there. Where does cos x equal 0? Cos x equals 0 here, and cos x equals 0 here. In other words, you can't have 0 degrees, 90 degrees, 180 degrees, or 270 degrees. So you could write them in angles like that, but since it has the 2 pi, you should probably do it in radians. So this in radians is 0. This in radians is pi over 2. This in radians is pi, and this in radians is 3 pi over 2. These are your restrictions right here. X cannot equal any of those. Okay, next one. 1 over 1 plus cos x plus 1 over 1 minus cos x. And we're going to get restrictions again. Again, I would get a common denominator. So it's a bit of a crazy common denominator, but what's the common denominator? It is 1 plus cos x times 1 minus cos x. Okay, what do you have to multiply 1 plus cos x to get all that? You have to multiply it by 1 minus cos x. So you better multiply the top by that as well, and you end up with 1 minus cos x. Right? When you multiply 1 times 1 minus cos x, you get 1 minus cos x. I'll put it in brackets for now. Plus, what do you multiply 1 minus cos x to get all this denominator? You multiply it by 1 plus cos x, so you better multiply the top by that as well. So 1 times 1 plus cos x is 1 plus cos x. Okay, on the top, we can do some combining. We have 1 plus 1, so we get 2. And we have negative cosine x plus positive cosine x. Those cancel. All we have on the top is 2. On the bottom, you can do your mountains and valleys again. 1 times 1 is 1. 1 times negative cos x is negative cos x, and positive cos x times 1 is positive cos x. Those cancel out again. And then cosine x times negative cosine x is negative cosine squared x. Okay, 1 take away cosine squared x. That looks encouraging. Let's go back and look. 1 take away cosine squared x. Yeah, there it is, right? 1 take away this cosine squared x, just like we did before. It's the same as sine squared x. So what we have left is 2 over sine squared x. It's a very good answer. What we like, though, is we like having no denominator. So if you think about this, this is the same as, I don't know, I'll just write here. It's the same as 2 times 1 over sine squared x. What's 1 over sine squared x equal? Well, 1 over sine is the same as cosecant. So 1 over sine squared x is the same as cosecant squared. So our final and even better answer here could be 2 cosecant squared x. Okay, restrictions. Look at this, and your denominator can not equal 0. What would make the denominator equal 0? Well, you're multiplying this by this. If this first bit, 1 plus cos x, if that equaled 0, you'd have 0 times something, the whole denominator would be 0. You can't have that. Same with the second one. If you had 1 minus cos x equaled 0, you'd have something times 0, which equals 0. Your whole denominator would equal 0. You can't have that. So here's your 2 restrictions. What do we know? Well, we solve this. So if 1 plus cosine x can equal 0, then move the 1 over. Cosine x cannot equal negative 1. If 1 minus cosine x can equal 0, move the negative cosine x over. You'll get cosine x cannot equal 1. Okay, cosine x can equal negative 1 and cosine x can equal 1. Where does cosine x equal negative 1 and 1? It equals negative 1 right here and positive 1 there. So in other words, cosine x cannot equal 0 degrees or 180 degrees, or if we do it in terms of radians, x cannot equal 0 or pi. It can equal that. It can equal any other angle except for those ones. All right, last one. We're going to simplify this. Wow, this looks a little complicated. So if you get confused, I really recommend the first thing you do is switch everything to sine and cos. So tan squared x is sine squared x over cosine squared x. Then we're going to take away this sine squared x. And what's it over? Might as well put a denominator. It's over 1. All of that divided by tan squared x again is sine squared x over cosine squared x, and we're going to multiply that by sine squared x over 1, I suppose. Okay, on the top we want to get common denominators, and the common denominator is cosine squared x. So the first one already has that denominator. It stays the same, sine squared x. The second one, what do you need to multiply by to get cosine squared x? You have to multiply by cosine squared x. So you have to multiply the top by that too. You end up with sine squared x times cosine squared x. And now that has a common denominator of cosine squared x. So we've dealt with all this so far. Now we have to do the bottom part. So it's all over. Okay, we're just multiplying here. So sine squared x times sine squared x is sine, anything squared times another thing squared is to the now fourth power x, over cosine squared x times 1 is cosine squared x. Okay, this means divide here, so let's divide our fractions. We have the first one, and in fact, well, we'll do it in 2 steps, I guess. We have sine squared x minus sine squared x. That should be a hint of what you're going to do next. Cosine squared x over cosine squared x. We're going to flip and multiply, so we're going to have the cosine squared x on top and the sine to the fourth x on the bottom now. This is good news because these cancel. Alright, do you see what you can do on the top here? You can take out a greatest common factor. What's the greatest common factor? It is sine squared x. What are you left with when you take that out? Well, sine squared x times 1 equals sine squared x, and sine squared x times cosine squared x equals sine squared x cosine squared x. This is all over sine to the fourth x. Alright, what do you want to do next? Well, let's take a look at this 1 minus cosine squared x. I think we've done this a couple times already. Yes, we have. 1 minus cosine squared x is the same as sine squared x. So, this part right here is the same as sine squared x. So this is great. We have sine squared x times sine squared x over sine to the fourth x. You can probably see the answer already, but in case you can't, sine squared x times sine squared x is sine 4 to the fourth power x divided by sine to the fourth power x. What? After all that, our answer is, these cancel out. Does that give 0? No. When you cancel out, it gives 1. Our final answer in this case is 1. This is amazing news. This means if you wanted to know what this equaled for different angles, you could put the value of the angle in here and here and here and here, subtract here, multiply here, divide, or you could just know that the answer will always be 1. Always, always, always. Except in which cases? Except for the non-permissible values, which we're not going to talk about in this case, for whichever ones are restricted, like we found the restricted up there. Okay, there you go. That's what you're going to be doing here. Have fun.